As you remember, we formulated the assertion that the estimate by integration by parts technique remains valid as long as the exponent function is real and monotonous inside the integration segment. So it's something like this or this. The exponential function itself decays very fast due to the largeness of lambda parameter. So it's no wonder the integral accumulates its value at the boundary. Now let me explain briefly why this estimate, meaning integration by parts, falls through if the exponent function f of x has an extremum, say maximum x naught, somewhere inside the integration segment. The devil is hidden, of course, in the remainder term. Let's take the general form of the remainder term after the first integration by parts. Here it is. We are going to discuss the estimate of such expressions in the next lecture. At the moment, let's just notice that the exponential term is dominated by its value at x naught, and not at the endpoints of the integration segment as before, when we dealt with monotonous function. Inevitably, the remainder term r is going to be proportional to e to lambda of f of x naught, which is exponentially larger than the contribution coming from the endpoints in the integration by parts technique. This is the reason why the error of the method of integration by part is exponentially large comparing to the main contribution, proportional to e to lambda f of a or e to lambda of f of b. This is why the estimate doesn't work for non-monotonous functions. However, it may still work for simple complex functions. Our last example is exactly about this. This time we are going to estimate the oscillating integral at large lambda. Here it is. Here lambda is a real parameter. First of all, we split the cosine into the sum of exponentials. So now we have two integrals. And we work the integral in such a way that it contains just a single exponential. One should always try to achieve it. The reasons are hidden deep inside the roots of complex analysis. We'll provide the details later. So we change x to negative x in the second integral, change the limits of integration accordingly, and finally, combining two integrals, we arrive at just a single integral on the segment from minus pi to pi. And this integral has an exponential function instead of a cosine. Now we perform integration by parts. It's quite typical. We simply play with exponential function again. So no details here. We just make two steps in a chain. So this is the first step. And this is the second integration by parts. And here are the first two terms of our asymptotic expansion. And finally, the plots. Again, look into supplementary materials for Wolfram Mathematica code. Here is the exact function, and these dotted lines is our asymptotic approximation. Perfect. Pay attention, this time our exponent function was complex but monotonous and frankly speaking very simple. And integration by parts technique worked just great even when describing the oscillating behavior. The last thing I'd like to discuss is the general half-heuristic rule of error estimate, which you can use in most cases when you are dealing with asymptotic series. Suppose you build some series, by integration by parts or whatever. Then, depending on the nature of the integral, the standard form of the asymptotic expansion can look like this. It's some series in 1 over lambda. It may be multiplied by exponentially large or small factor. And there is the last term, which is an error or term expressed as some integral. But the point is, every other term in our asymptotic expansion basically comes from the attempt to estimate the error function. Here it is. Trying to evaluate the error with better and better precision, we add more and more terms into the series. And this is how the series shapes itself. So the typical situation is that the error estimate is equivalent to the addition of one more term into the series. Of course, such things can be said for not very large n, when the series still approaches the real value of the exact function I of lambda. As you remember, the error is not a monotonous function of n. So this kind of argument for the estimate holds for n less than or an optimal number. So roughly speaking, if we have n terms in the series, where n is equal or less than the optimal number of terms, then the error term can be estimated to be of the order of the term with number n plus 1. So, for example, to build a super asymptotics, just derive the formula for the nth term, set its number to n plus 1, and get the error, and then minimize it with respect to n. This is how you obtain optimal number of terms in most situations. So, we discussed in detail the fundamental properties of asymptotic series using simple examples. The example with incomplete gamma function even allowed us to build both Taylor and asymptotic expansions and to show the effectiveness of the last one. The last example with cosine function showed that even oscillating behavior of the exact function can be recovered with just 2 terms of an expansion with an amazing accuracy. And the only magic we used was just elementary integration by parts. The next topic will give you more advanced tools for dealing with more interesting integrals and beautiful examples. So I hope you enjoyed our introduction and stay tuned.